In this video, I am going to talk about two concepts. One is concavity, and then I'm going to use the definition of concavity to define inflection points. Let's look at a graph. So let's say this is my Cartesian coordinate system or xy plane, and I look at the function, let's call it square root of x. Y is equal to square root of x function. So let's go ahead and draw tangent lines to different points of this graph. As you go to the right, what happens to the tangent lines? The tangent lines, they are sloping down, meaning that the slope of the tangent lines are decreasing. What it means is that if you have a function, let's call it g, which happens to be tracing the f prime, that means following exactly equal to f prime, which is the slope of each of these individual points, okay? I mean, slope of each of these individual tangent lines. Then if you graph it, what you're going to expect to see is that it's going down, something like this, because the slope of each of these tangent lines is going down. So the graph is going to be going downwards, all right? Now, let's go ahead and use this as my new function, and I'm going to go ahead and take the derivative of it, or find the derivative of g. Now, this graph is going down, so the derivative must be less than 0. That's something you already know. If a function is going down or decreasing, then the derivative is negative. But what is g prime? G prime is nothing but f prime prime. That means you are taking the derivative of f twice. Here we are dealing with single variable, so order is not an issue. So I can just say this is this, f double prime. So if f double prime is less than 0, what we say that a function is concave down. Concave down. And as you can guess, when f double prime is greater than 0, we will call that function concave up. But I will show you an example. But before I do so, let me go ahead and explain something. If you look at this graph, what do you notice? All of these tangent lines are above the actual graph of the square root of x. All of these tangent lines are above the graph of the square root of x function. So what it is, there is another way of kind of defining concavity or concave down, sort of in a graphical way. So if tangent lines are above the graph of a function, of course, right? Graph of a function in some interval I, in some interval I, then f is concave down in that interval in I. So that's another way of kind of looking at the concave down definition. And this is just more graphical or visual way of doing it, and this is more mathematical way of doing it. Now, let me go ahead and look at this function. And this is a familiar function. It's the y is equal to f of x is equal to e to the power x, the exponential function. So the exponential function, look at the tangent lines again. Right here, right here, right here. As you look at these tangent lines, you can see they are increasing in the sense of their slope, right? So their slopes are increasing. So once again, if I were to define g as a function, which is f prime of x, or the derivative of f, then we looked at G, we notice that G is increasing, so G is gonna look something like this. All right. So now G is increasing on some interval, right? Then in that interval, G prime or G prime of X must be positive or greater than 0. Oh, by the way, what is G prime? G prime is nothing but F double prime. F prime of prime, which I can say just F double prime, because we are dealing with single variable, which is greater than 0. So if F double prime is greater than 0 for a function F on some interval, we call it concave up. So this is a concave up function. Now that's the mathematical way of defining it. Now let's go ahead and do the same thing graphically as we did for the other guy. So look at each of these tangent lines. All of them are below the graph of the function, which is e to the power x. So if you have tangent lines that are below the graph of the function on some interval, then f is concave up. Okay, so similar to this definition. If the tangent lines are below, if the tangent lines are below f on some interval I. Okay, if tangent lines are below f or the graph of the function f on some interval I, then f is concave up. Now let me take these ideas of concavity, concave up and concave down, and apply it to a new function. So I have a function that looks kind of like this. This, by the way, is a very famous function. In case if you don't know, or you may already know, it's 1 over 1 plus e to the power negative x. This function is powerful for many reasons. In the business world, the graph of this function could represent a business cycle. Okay, it could represent a business cycle. Initially, the slope is small. So if you look at the left side, the slope is very close to 0, right? Very close, changing slowly. But over time, a business initially struggles, but over time, at some point, it starts to pick up. The slope starts to pick up. Okay, so it's growth. So this is the growth state of a business. I am kind of sidetracking, but it's good. So you get to see how math is applied in the context of solving real world problems that are very meaningful to you. So this is the growth period of a business. This is the struggling period of a business. This is the growth period. Now, if a business grows at some point, so it grows a lot for several years, okay? But at some point, that growth is gonna slow down. So now the slopes are gonna be like this. Slopes are getting smaller, or the derivatives slash slope of the tangent lines are getting smaller. Now this region, by the way, is the established business slow growth. Established business with slow growth. They are growing, but with slow growth. Okay, so now the growth here is positive, a lot of growth. Growth here is slowing down, but still growing. And this point is called inflection point. Actually, without realizing, I kind of used this example as a way to define inflection point. Inflection point is a point where the concavity changes. So this is concave up here in this region, concave up, okay? Here in this region, concave down. So here it is concave down. So concavity changes. So when concavity changes from positive to negative or negative to positive, then the point at which it changes, which is right here, is called inflection point. Or it could be the case that you can look at it another way. It goes from concave up to concave down, or concave down to concave up. Either way, it doesn't matter. So it goes from f double prime greater than 0 to f double prime less than 0. Change in concavity. It could go this way or it could go that way. Actually, that way. That's what I meant. The other way. So that's change in concavity. So that's what we say. That's when we say that a function has an inflection point. However, back to our example, I kind of want to talk about this example a little bit. So this is a business cycle. There is a famous Harvard professor, I think he explained this thing in one of his books. I forgot his name. He's from Harvard Business School. He takes this function and explains the growth cycle of a business. So you can think of big corporations like Apple, Microsoft, Google. They went through these steps at some point in their lives, business cycle. Okay, and then there was a period of rapid growth. Now these corporations are big corporations. They are in this region where their growth is slow. They are growing, but slowly growing. It's not like the growth in this region where growth is very fast. Okay, so this is what an inflection point is, where the concavity changes. So in this video, I talked about the definition of concavity from two perspectives. In terms of mathematical definition, where f double prime greater than 0 means concave up, f double prime less than 0 means is concave down. Okay. And also from graphical point of view, if the tangent lines are above the graph, it's concave down. If the tangent lines are below the graph, it's concave up. And inflection point is a point where the concavity changes, either goes from concave down to concave up or concave up to concave down. Oh, by the way, this function, I can't stop talking about it. This is another interesting function that is used also in machine learning or AI, artificial intelligence. This is what we call an activation function. Okay, so this function is very useful in machine learning, in the world of deep learning, machine learning, or artificial intelligence. This is called an activation function. Activation function. So very useful. I hope that this discussion was helpful. Thank you very much.